First of all, thank you, Benedin, for the invitation, for the opportunity to be here. I'm new to machine learning, but I would like to talk. I would like to say a few words about our attempt of applying Gaussian process modeling in sampled dynamics. This is joint work with Marcio Gameiro, Ying Hung, William Kallis, Konstantin Mishaikov, and Everton Vieira. Marcio, Ying, and Everton are from Konstantin's group at Rutgers. Bill is from Toledo University. And we propose a framework combining topological dynamics and statistical surrogate modeling with uncertainty quantification, to which it's possible to characterize global and local dynamics with rigorous bounds on the confidence that the characterization is correct. The characterization is derived from data, where it's assumed that data is generated by an unknown continuous dynamical system. Okay, let me say that in such a way. The traditional focus of dynamical systems is on understanding the structure of invariant sets, and in general, to correctly capture the invariant set may require correctly identifying the non-linearity generated dynamics to an extremely high level of precision. And the logistic map and the associated cascade of period doublings is an archetypal example. However, to the confidence of correctly identifying the nonlinear map from finite data decreases rapidly as a function of precision. For this reason, our approach focuses on coarsely characterizing the dynamics rather than identifying the generator of the system. And the characterization is given by the Conley index, an algebraic topological invariant from which one can induce the existence of invariant sets and the dynamic structure of invariant sets. For instance, one can induce the existence of fixed points, periodic orbits, heterocyclic connections, or chaotic dynamics. In essence, our strategy is straightforward. The scheme is as follows. Assume that we have observed data that have the form of pairs xy. Y is the image of an unknown continuous function f. And we assume here that f is a realization of a Gaussian process with some pre-specified kernel, with some vector of parameters which are unknown. In the figure on the right-hand side, I present one-dimensional example to give you geometric intuition about what we are doing. So assume that we have the data which are marked by red dots here. And given the data, we estimate parameters of the kernel and construct a Gaussian surrogate model with predictive mean and covariance function. And here the mean is shown in black. Next, in order to make computations feasible, we discretize the space. So we choose a finite cell complex whose geometric realization is our domain of interest X, and we construct a multi-valued map from X into X, multi-valued map which we identify with its graph, with the following properties, namely G is geometric realization of products of cells, and second, for each point X, the value is non-empty and contractible. So on the right-hand side, the region G is composed of squares of size 2 to minus 10 and is in blue. Next, we use this multivalued map G to identify the potential dynamics and compute the associated Conley indices. The result of computations is on the left-hand side. In the bottom here is the Conley-Morse graph, and here we also present the invariant set in corresponding colors. So Conley computations are made for multivalued map G. So the probability of the inclusion of this inclusion yields confidence of the correctness of the computation, and we are interested in highly confident results. Therefore, we modify this multivalued map G to both preserve the dynamics of interest and maximize the probability of this inclusion. So on the right-hand side, the computations are performed for 95% of confidence. So what we can see here, starting from relatively few data points, we are able to identify B stability. Here we have repelling point, and somewhere here we have attractors. Okay, how we do that? On the next few slides, I have very basic stuff concerning Gaussian processes. So let me go through this very quickly. In case of d-dimensional problems, we look at our data component-wise, namely, we construct d Gaussian processes for one component function. We estimate parameters of the kernel. Any estimation method can be used. In our experiments, we use just maximum likelihood estimators. Here we have standard formulas for the parameters. And now the prediction for any untried point in the space can be obtained as d-dimensional multivariate distribution. This is the mean vector, and this is the best linear unbiased predictor. Here are again standard formulas for the mean function, which is the expectation conditioned by the data, and the same about the variance. And recall again, also that if we have a multivariate normal distribution, then the squared Mahalanobis distance, which has the form of this quadratic form, has a chi-squared distribution with d degrees of freedom. D is the dimension. So the same, if G is a Gaussian process, so the same applies to any value of this G at any point. So now let me define a confidence ellipsoid. Here is the definition of ellipsoid. I mean, the ellipsoid will be the set of points that are within the C distance within the mean, in the sense of the squared Mahalanobis distance. Since when we put as a radius of this ellipsoid the quantile of order 1 minus delta of the chi-squared distribution, then we have this condition, namely the probability that G at point X belongs to this ellipsoid is greater than 1 minus delta. Therefore, I will call such an ellipsoid a confidence ellipsoid and call 1 minus delta the confidence level. And it's almost straightforward to see that when we have any finite subset of the space and any delta, which is responsible for the confidence, then we can choose radii for confidence ellipsoid such that the joint probability that G of V falls into the associated confidence ellipsoid for all the points of the set S is greater than 1 minus delta. And in our construction, we make use of these pointwise bonds, and we insist that the multivalued map that we construct satisfies this condition, namely at each point of set S, which in practice is it may be the set of vertices of our cell complex or set of barycenters. It depends what we choose. So at each point, we insist that the value of this multivalued map G covers the confidence interval. Okay. To obtain the appropriate conditions on values of G on the remaining set, we restrict our attention to kernel functions that imply high probability bands on partial derivatives of sample paths. I mean, this means that we restrict ourselves to kernels that are, for instance, 4 times differentiable. So the standard examples of such kernels are squared exponential covariance function or Matern function with parameter greater than 2. And in such a case, there exists constants A and B such that for large enough capital L, this condition holds, namely the probability that G is L Lipschitz is greater than this term. Okay, so we can see that when capital L grows, the term on the right hand side grows to 1. This condition is kind of weaker version of Lipschitz continuity. This condition does not prevent G to oscillate from oscillating too fast, but it says that such fast oscillations have low probability. Okay, and we use those two, I would say, ingredients, namely confidence intervals and this high probability constant Lipschitz in the construction of our map G, namely take a top dimensional cell and consider ellipsoid at vertices of Xi where we decided to consider confidence intervals. We enlarge this confidence interval accordingly, I mean according to this constant capital, how probability Lipschitz constant capital L and the diameter of the cell. Okay, we take this information over all the vertices of sigma where we have the confidence intervals. We cover this set by our cells, and we define the graph of this multivalued map as the union of such products. Okay, and this is main result which characterizes properties of the map that we construct, namely under the same assumptions as before. Alpha will be responsible for size of values of this multivalued map. Delta is responsible for confidence, epsilon for graininess of the cell complex, and n is the cardinality of the data set. So we can prove that for any alpha and delta, there exists epsilon and such that this multi-valued map that we construct satisfies these two conditions, namely the probability that the diameter that the supremum of diameter of values of G is less than alpha is greater than 1 minus delta, and the probability of the inclusion of this inclusion is greater than 1 minus delta, provided that we have the cardinality of data is greater than n0, and that the diameter of our cell complex is less than epsilon 0. Okay, so this is a kind of asymptotic property of our construction, which says that, which implies that with sufficient data and sufficient computational effort, we can obtain the following two fundamental results about map G, namely the detailed dynamics can be extracted from this multi-valued map G via Conley-Fiore computations because the sizes of values of G are small, arbitrarily small with high confidence. And second property says that the dynamics that we identify occurs because of this inclusion, and in particular, the confidence that the identifying dynamics is valid for F is also greater than 1 minus delta. Now let me give you again geometric intuition about how this construction works. So I will say a few words now about very specific one-dimensional construction, just to be able to present the graph of this map. So now the discretization of our interval consists just of vertices and edges, and consider midpoints in every other edge. I mean midpoints in odd-numbered edges only, and we start with data. We fit the Gaussian process. On the right-hand side, we can see the mean of this the Gaussian process, and we fix delta and choose confidence in the intervals in the odd-numbered vertices. Okay. And now we construct the multi-valued map in two steps. First step concerns odd-numbered edges, namely we cover the confidence intervals by the smallest union of cells of our complex. So in this case, we have the uniform grid. So the map is going to be a cubical, just the cubical map, yeah? So you can see these values of the multi-valued map in blue. And next we define the map in the remaining edges, on the remaining edges, namely consider capital L to be the high probability Lipschitz constant, and at each endpoint of the confidence interval, we draw the lines, the rays, with slopes plus minus capital L to the right and to the left. So the meaning of those, let's say, Lipschitz cons is that with high probability, our function, our Gaussian process between this point and this point lies in this region bounded by red contour, okay? And the definition of the multi-valued map in these edges is the following, namely, again, we take the smallest possible union of cells that cover the cone. So this is the construction. Accordingly, what we have, namely, we have that this probability that G, actually the probability that Gaussian process lies in the region bounded by the red contour is greater than 1 minus delta. This does not necessarily mean that the Gaussian process is included in this graph, but it implies that its graph lies in the epsilon 2 vicinity of the graph, okay? Which is totally enough to make conclusion about the dynamics of small g from computations coming from this multi-valued map because of one of our results with Konstantin, Marian, and Mateusz Przybylski. So this is this special this special construction in dimension 1, and now I would like to show you some experiments concerning exactly precisely this construction. We tried a logistic map, so we sample a few points, just 4 points from logistic map with parameter value 3.15. So we know the dynamics of this system. Namely, we have 2 unstable fixed points, and all other initial conditions limit to a stable 2 periodic orbit with these parameter values. And on panel A, I present the construction of this multi-valued map G, composed of squares with size 2 to minus 10, and the Conley index M0. Here is the Conley-Morse graph. Conley index of this set in blue here identifies the existence of fixed point with probability 95%. So this is true. However, with this confidence and this resolution, of the mesh, we don't see the 2 periodic orbit. As a remedy, we can divide the mesh. We refine the mesh, so we take twice more cells in the same interval and perform the same computation, the same construction on the same confidence level, again 95%. And now you can see that we are able to identify 2 periodic orbits. Okay. So now one can ask question: what about the confidence? This is for 95% of confidence. Now the question is it again true with confidence, let's say 97.5% or not? So on panel C, we can see computations for confidence 97.5%. And as you can see, again, with this confidence level and the same grid size, we cannot identify 2 periodic orbit. Probably going to final mesh would solve again the problem, but I would like to say about another concept of refining the result. Namely, we can, as you remember, we consider set of confidence intervals with the property that the joint confidence is high, but the confidences of particular intervals don't not necessarily be the same. So after identifying something interesting is taking place here, because we identified that this is invariant set in this place, we can consider smaller confidence intervals over this set and bigger ones outside, such that we keep the confidence on the same level, but we distribute the confidence differently. And as you can see, in this case, it works, namely with the same confidence, the same size of the grid, but non-uniform distribution of the confidences of intervals. We can identify two periodic orbit in this case. Okay. So what is interesting, namely, we have some conclusions starting from sparse data, and as you can see, the prediction is not very precise here, but it turns out that it's enough precise for topological invariants, which are robust to still have correct conclusions about that. Another example is for again for logistic map with different parameter value, and now we have more points. Then the accuracy of the prediction is, as you can see, is much better, and we do the same construction, but the multi-valued map is very skinny now, yeah, because the prediction is very good. But as you can see, we can identify the existence of four periodic orbit for this logistic map, starting from our construction. And when we inspect the Conley indices, namely the Conley index of this unstable fixed point, and this Conley index of two periodic orbit, using the additivity property of the Conley index, we can also show the existence of connecting orbit from unstable fixed point to periodic orbit. Another example is for chaotic dynamics, namely we sample few points from this map. We take 10 sample points. We divide interval 0, 1 into 2 to power 10 pieces, and we take confidence to be 95%. And now we, from our construction, we can see the existence of invariant set here in orange, which has trivial Conley index, but when we look at the index map, we can prove that we have chaotic dynamics here. Thank you very much for your attention.
Thank you.